Myself, Madhu S., Assistant Professor of Physics, Government First Grade College, Srinivaspur. I would like to discuss on topic Scalar and Vector Fields, Paper 301, Electricity and Magnetism for BSc Physics, 3rd Sem, Bangalore North University, session number 31. Learning objectives from this topic: scalar field, vector field, gradient of a scalar, meaning of del operator, relation between electric field and electric potential. Course learning outcome from this topic: understand the differences between scalar and vector field and the concept of gradient of a scalar function, physical significance of grad phi. First of all, we shall understand what is physical quantity. The quantity which can be measurable. Example: mass, length, time, temperature, electric field, electric potential, force, displacement, acceleration, and so on. Once again, I repeat, the quantity which can be measurable. Whereas for non-physical quantity, we cannot measurable. Example: sadness, happiness, angry. In nature, for certain quantities, we can be measurable, whereas certain quantities we cannot be measurable. Physical quantities may be classified into two types: scalar and vector quantities, both function of time and position. In this slide, you can see positive charge and negative charge. From positive charge, electric lines of force are diverging, whereas at negative charge, electric charges are converging. But in between, some electric field are uniform, but at some this region, electric field are not in uniform. Electric field of a point charge near the charge, electric field value is large. As we go away further from the charge, electric field goes on decreases with respect to negative or with respect to positive. But electric field is a continuous function with respect to position of point in that space. Next, we shall understand what is field. Field which specifies a quantity everywhere in a region. Therefore, between 2 point charges, the force exists between them is electric field. Electric field of a point charge varies from one point to another point, but electric field is a continuous function of a point in the space with respect to this line or with respect to this one. In the case of magnet exists two poles, north pole as well as south pole. Magnetic lines of force begins or diverges from north pole, converges at south pole. In this slide, you can see from positive charges, electric lines of force acts diverging. Next, we shall discuss on the topic scalar. Scalar is a physical quantity which completely describes its magnitude. If the quantity which is completely described by a magnitude are called scalar quantity. Example, mass, temperature, density, so on. Next, vector quantity. A physical quantity which has both magnitude and a direction is called vector. Example, force, velocity, electric field, so on. Next, new topic. Scalar field, a region of a space in which scalar quantity is continuous. In the beginning slides, the field, if it is continuous and is defined by a single value at every point of the position variable, is known as scalar field. If phi is a scalar function and position variable r with a set of coordinates x, y, z, then we can denote scalar field as phi of r equal to phi of x, y, z. Example for scalar field, variation of temperature. In a metal rod, one end of which is heated while other end is kept cold, that is example for variation of a temperature of a metal rod for scalar field. Temperature varies along the length of the rod. Similarly, variation of electric potential at various points surrounding a charged body is example for scalar field. Next, we shall discuss on the topic vector field, a region in which vector quantity is continuous and is defined by a single value in magnitude and a direction at every point of the position variable is called vector field. If v is a vector function of position variable r with a set of coordinates x, y, z, then vector field can be denoted as v of r equal to v of x, y, z. Example for vector field is electric field. Force experienced by a unit positive charge placed at any point in the field gives magnitude of vector field, and a direction in which unit positive charge moves gives direction of vector field. To understand the concept of a vector field varying from one point to another point with respect to charge, it requires both magnitude as well as direction. Similarly, object which is rotating about an axis, velocity of an object moving, rotating is example for vector field. A body which is rotating about an axis, velocity is different at a different point if it is in circular motion. Therefore, velocity is the function of position of a point. Next, we shall discuss on the topic gradient of a scalar function. Consider a point P in the scalar field having position vector r equal to xi cap plus yj cap plus zk cap. And let the value of scalar field at this point be phi of vector r equal to phi of x, y, z, where phi of x, y, z is a continuous differentiable function of three independent space coordinates such as x, y, z. The partial derivative of phi with respect to x can be written as dou phi by dou x. Similarly, partial derivative of phi with respect to y can be written as dou phi by dou y. Partial derivative of phi with respect to z equal to dou phi by dou z. Dou phi by dou y represents rate of change of phi at the point P along the y direction. Dou phi by dou z, rate of change of phi at point P along the z direction. Whereas partial derivatives dou phi by dou x, dou phi by dou y, dou phi by dou z, we can construct at each point in space vector whose component along x, y and z direction are equal to respective partial derivatives of scalar function. This vector is known as gradient of phi or grad phi. Therefore, grad phi can be written as grad phi equal to I cap dou phi by dou x plus j cap dou phi by dou y plus k cap dou phi by dou z. If we taken common phi, then we can written as grad phi equal to within the bracket I cap dou by dou x plus j cap dou by dou y plus k cap dou by dou z. Therefore, grad phi equal to del phi. Grad phi equal to del phi. Del is called, the symbol del is called del operator. It is not a vector but an operator which obeys the laws of vectors. Therefore, del equal to I cap dou by dou x plus j cap dou by dou y plus k cap dou by dou z. Del, gradient of scalar function, nothing but grad of phi equal to del phi. Relation between electric field and electric potential. By the definition we know, electric field is defined as electrostatic force experienced by unit positive charge. Therefore, electrostatic force equal to minus q naught vector E. Work done to move the test charge in the electric field along vector dl is given by dw equal to vector f dot vector dl. In place vector f minus q naught vector E dot vector dl. This can also be written as dw by q naught. If q naught is cross multiplied, then expression reduces to dw by q naught equal to minus vector E dot vector dl. We know by definition dw by q naught is nothing but potential difference dV between the 2 points, which represents amount of work done in bringing unit positive charge. Therefore, equation 2, dV equal to minus vector E dot vector dl. If the coordinates of 2 points x, y, z and x plus dx, y plus dy, z plus dz respectively, then potential difference between 2 points can also be written as I cap dou v by dou x plus j cap dou v by dou y plus k cap dou v by dou z into I cap dx plus j cap dy plus k cap dz. The quantity is called grad v or del v. The quantity which represents is called displacement vector dl. Therefore, in this place we can written as del v, in this place dl vector. Therefore, dv equal to grad v dot vector dl. Comparing equation 2 and 3, vector E equal to minus grad V. Important. Vector E equal to minus del V. Summary of this session. We understood the concept of a scalar vector field with example, mathematical representation of del operator, meaning of gradient of a scalar function, physical significance of grad phi, relation between electric field and electric potential. Next we shall move on for multiple choice question in which the topic arises. First question, the gradient can be replaced by which of the following? Option A, Maxwell equation. Option B, volume integral. Option C, differential equation. Option D, surface integral. Option C is the correct answer. Gradient can be replaced by differential equation. Option 2. Second question, multiple choice question. The gradient of xi plus yj plus zk is option A 0, 1, 2, 3. Option D is the correct answer. Phi value xi plus yj plus zk. If we differentiate with respect to x, value is 1. If we differentiate with respect to y, 1. If we differentiate with respect to z, 1. 1 plus 1 plus 1 value 3. Question number 3. Del operator is also known as option A, divergence operator. Option B, gradient operator. Option C, curl operator. Option D, Laplacian operator. Answer B is the correct answer. Del operator is also known as gradient operator. Fourth one, electric field can be written as option A, negative gradient of V. Option B, negative Laplacian of V. Option C, Laplacian of V. Option D, gradient of V. For this question, answer A is correct. Vector E equal to negative potential gradient or negative gradient of V. Fifth one, find the gradient of the function x square plus y square plus z square. Option A, I plus j plus k. Option B, 2i plus 2j plus 2k. Option C, 2xi plus 2yj plus 2zk. Option B 4xi plus 2yj plus 4zk. Option B is the correct one. Let us discuss and let us solve if we differentiate x square with respect to x. 2x is the answer. If we differentiate y square with respect to 2y, 2y is the answer. If we differentiate with respect to z, 2z. If we differentiate with respect to 2y and z, this term becomes 0. We know x value 1, y value 1, z value 1. If we differentiate x square, 2x becomes. If we take x value 1, 2 into 1 value 2. Therefore, 2y, similarly for y square, 2y, y value 1, for z square, 2z, z value also 1 in the given question. Therefore, option B is the correct answer. References to prepare this session. Thank you.